Hi, everybody. Welcome to the second webinar of 2024 of the Brazilian Society of Automatics. I have the great pleasure to introduce Professor Itzhak Barkana. Professor Barkana, thank you very much for accepting our invitation to give us this seminar. Before introducing Professor Barkana, I would like to give you some information. First, the seminar will be recorded, and everybody can access the seminar after in our web page. And also, if the audience has some questions to make to Professor Barkana, you can write in the YouTube chat, and after I can read the questions for Itzhak after his presentation. Okay? Let me introduce the professor. Itzhak Barkana received his bachelor and master degrees in electrical engineering from Technion Israel Institute of Technology and his PhD degree in 1983 from Rensselaer Polytechnic Institute. He presently is a consulting for the high-tech industry after retiring from his job as a fellow with Kulik and Sofa Industries in the United States. Between 1988 and 2000, he was also been visiting an adjunct professor at Drexel University in Philadelphia. In 2002, he received the Benjamin Franklin Key Award from the Philadelphia chapter of IEEE for advancing the theory and practice of adaptive control, and in so doing, making major contributions to improving the speed and accuracy of specialty robotics for the semiconductor industry. He is co-author of the book Direct Adaptive Control Algorithms, Theory and Applications, and has published 3 chapters in books and more than 100 papers in journals and in major technical conferences. Now, Professor Itzhak, thank you very much. Thank you again for accepting our invitation. And now you can begin your seminar.
Okay, after the introduction, thank you very much. I'm Itzhak for all. No professor, no doctor, no son, no mister. And ladies and gentlemen, Brasileiros, I have no words to express my pleasure and my honor for being invited. I know a few guys in Brazil. I didn't visit much except for the Iguaçu part of the Brazilian part of Iguaçu, well, once in one of my trips. However, I know a few guys, and now let's start talking. You can see my lecture.
Yes.
I called it, I want to give you an idea about things that allow better performance. First of all, I called something adaptive control simple. The word simple made some people nervous, and people's papers were rejected until people got used with it. And you can have adaptive control simple. But then we had some new problems. The people said that the proofs of stability analysis don't work unless you have those conditions. So the result forced me to go to very good, very high level math and to review things. And as I said, I play professor, but what I am is I'm an engineer. And if you see by the years that I finished PhD a little bit late, after I had some engineering work and experience. And I went there because people wanted me to be a doctor. I couldn't care less. I went to America because I wanted to learn some better English. But it changed my life because you discover that good engineering mind, good experience is good and good ideas, but they may not work in things that change. So you need more. So as I said, my idea is to try to apply what we know and to have good control. Faster machine, faster plan, faster this. And what you said about Kulik and so far was a very good application. But when you start working, you have a good linear time invariant system, pole zero, everything's all right. Once you start moving, things become time varying or nonlinear. I put them the word non-stationary to contain both. All of a sudden, the analysis is not what you said, and you start having problems, stability analysis. And you hear about things like passivity and so on. And then people required adaptive control. Start with something simple, didn't work, and they moved to some great guys, developed some nice, good mathematics, but they required adaptive control of the same order as the plant. Now, in the paper, you can assume that your plant is of second order or third, but our application, the order could be 50. And so you need, for a single input output, you need some 50 gains. For multivariable, they don't exactly know what. So my problem was that I had a large flexible structure application. And this was also the grant of my advisor. So we tried to do something. By 1980, to implement adaptive control for a plant of such order and multivariable was impossible. So we developed some simple adaptive control, started slowly. We wrote papers, we tried some application. People at JPL used it because they couldn't use something else in work, but still, we were not sure, so we had to develop the mathematics. So first of all, why do we need adaptation? First of all, what do we want? We want fast response, precise. And people can do on the machine, you know the transfer function of the machine, the equation, then you can do some tuning. And then I thought, why not automatic tuning? Because manual tuning, it's problematic, and then adaptive control. We'll talk about everything. So a simple example, just to express some ideas of control, of good control, before any adaptive. An example, people had such an example for both. They were doing a step input, step command, and the boat took some 20 seconds or so to converge. And they asked me, can you try to do faster? And they say, it takes 20 seconds, then why do you give a step command to a plant? What do you mean? Step is immediate, it's the fastest command. All right, but if you have limitations, so sometimes try to smooth trajectory. Because or observe, so they say engineering is needed. Observe that you can use the derivative of your trajectories, you can make better trajectory following. What happens when you give the step response? The current wants to go to very high to give you immediate, fantastic acceleration and velocity to reach the position, but you reach the limitations. So I said, let's try something nicer. 20 seconds, this is what I give, 20 seconds. All right, so when they saw my first result, they started laughing. So we must compute some complicated trajectory only to lose. I say, yes, but look here. Look here. You need some signal. This is the signal that moves the boat. Ignore this one for a second. You have an input, you have output, you have an error, and you use the error to move the boat. So you need some signal in order to move the boat. So this creates an error. It's something. If the gain is very large, then the error could be smaller. But a very large gain may disturb your plant. But what happens if somebody tells us what the error signal is going to be? for the given trajectory. Hey, how do you know? Who can tell you? All right. So this is our trajectory. I tried different stuff, even the 7th order polynomial. I ended with the 5th order. And this is the velocity, and this is the second derivative, acceleration, and if needed, we use some very high accuracy plan needed, so we use also J. But when you see here, why do you need the signals? Oh, let's look at the error. For this trajectory that I use, I look at this error. It's not perfectly symmetric like the velocity, but looks very much like the velocity. So I'm measuring this error, tracking error. And from the initial to along with the command, I send a velocity signal to the planet with some gain. You try 10, you try it's not enough, you try 20, it's better, you try 200, it's too high, the velocity, the error becomes negative, goes the other direction. So finally, you can find the right value. Okay, once you find the right value, you brought this signal, this peak to 0. Okay, so are we now perfect? No. You still have an error, but much less. Also, you look there, it looks very much like the velocity. I mean, in general, the second derivative. So if you have a smooth trajectory, those signals are smooth and don't create. The minimum time, it's perfect acceleration and minimum acceleration. But when you finish and you think you reached the whatever you wanted, any plane keeps oscillating until it stops oscillating. With the smooth trajectories, you avoid oscillation. So that's what you have. And I edit the acceleration and I see some small error. If you look well, it looks like the jerk, the derivative of the acceleration. You can leave it if you're satisfied. If not, you can add the second. And for the very precise application, I used it. So this is what happens. You have some optimal, this is some schematic. You have some plant that gives you the optimal trajectory. The output is here, but before the final integrator, you have the derivative, and you have the second derivative, and so on. So along with the signal, the normal, the simple control has an input, an output, error, and you deal with this. But this one now introduces the velocity and the acceleration signal, and all of a sudden we have a perfect tracking instead of this delay that you saw. But people laughed. Okay, so you have 20 seconds time response. So for 20 seconds you must do this complicated stuff. I say yes, but because I added something from outside, from the command, a signal, it's not a signal that requires the plant to increase. So the gain, you do the same, you have the same performance, perfect, not the same performance, you have perfect tracking, and the gain is much lower. So you can let the current. So you can let the current increase. We have here, instead of 20 seconds, 10 seconds. 50% of what used to be before. Not such a bad thing. And here the desired and the actual are about the same. The error is very small. If you can, as I said, add also the third derivative. Never mind here. But now, why I have to talk about adaptive control? We know how to do. No, the gains of your system are not perfect. And if you have a drop, you have the best tuning, some gain drops, and you have a big error. So I would like, if the gain drops, I would like to have another gain. So I call it adaptive. That's how it is. I'm talking here only about the idea of adaptation. So you can take you have some gain feed forward, KV feed forward. You have a number. You have some initial guess, can be 0 if you don't know anything, but we have some idea about the plan. So you measure the velocity, as I said, the peak velocity in the middle, and you change the old velocity with the new one, and you run the parameter. This is the tuning only, it's not the work. You tune it before, and you get a new KVFF, you see how it looks. Again, I said, could be larger, could be smaller, and so on, but you have an error until the KV is such that the error goes to 0. All right, then you run again, and you measure the peak, the new peak error, which is due to the velocity, and the same you tune, and the same if you want to do the jerk, and so on. So first of all, it's got to have a desired path that you want. If you affect the comment, if you decide about the comment. So properly tuned feed-forward signals are an external signal that give you the signal, the voltage, the signal that the plant needs without forcing the plant to do high thing, to use high error, to use high currents. So they are doing some manual tuning. The man was doing, so as I said, you have a command, you send it to the plant, you measure the position, and this is the error, you have the error, and so on. But they decided to add the tracking error, used to be here. This is the normal situation, but we take the derivatives of the command and we supply the feed-forward. So this is the total signal. We have the desired feedback plus the signal from the. And okay, so the machines, I'm talking now about where I used them. I went to a company where there used to be Curtin Sofa in Philadelphia, used to be first in the world. Then some Japanese company took it over, and then everybody decided that the technology was dead. That's what we get. You have the nominal trajectory and the real, actual trajectory with some errors. And you wait until you measure, because then bonding machines, in bonding machines, 1 micron error could be 1 micron oscillation in particular, can be 1 micron too many. They wanted good errors. They would do it and they would measure. And they said, say, try to tune the feed-forward. You tune per, I said, they tried. If you have a few machines, they can do it, but this company, those bonding machines are very well needed. So the company was doing some 500 machines per month, some 8,000 per year. So you cannot do it. So they would tune a machine and use the same parameters for our machine. And I came to ask, so this is what the situation when I came there. The nominal trajectory was 100 mils, 2.5 millimeters in 35. Practically, they were measuring the error was 45-50. And because of this error on the way, they were afraid not to touch the other wires. I mean, I'm talking about the bonding machine. You have an integrated circuit, you have a bond here, you connect it to external wall, and they could, the points could be not closer than 150 microns in the pattern. All right. So I said, why should you do it tuning? Why should you do it per machine? And they give you the algorithm. You do a trajectory, you press a button, and the button makes the machine run a trajectory with a given gain. You measure the error, do the new gain, you run it again, run it again, run it again. When the velocity is nice peak, when velocity error peak goes to 0, then you want to do this acceleration and so on. So that's what people showed me on a display. You have the initial error, and you see this velocity peak. You supply velocity, change, until this goes to 0. But then you see this acceleration, like signal, and you apply the acceleration, and you reduce the acceleration until this is automatic tuning. So instead of sending people all over the world to tune the machines, because if they, in Thailand, in Taiwan, they replace a motor, then you have to send people to tune it. I said, why should you put automatic tuning in the beginning? They said, Professor, keep writing papers. But they were in trouble. So I said, play a little bit. So I played a little bit, and then my first result was this: automatic tuning. You have the machine, you press a button, instead of people going to tune, you press a button, and the machine starts playing. Tuck, 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 until it's tuned. And you measure the error, and that's what happens. So my first result was that the tuning was good, and the time was 20. When they said that the time was 20, the vice president said, oh, you mean 20, you mean nominal. No. Now 20 means 20. You want 20, you get 20. So this is the first result, and then we managed to come down and to do better control and so on, take care of things. So instead of 45 actual, you have an 80 millisecond. And also this distance between the bonds started coming down and was 25 micron. So the company is not only back first in the world, but the technology, which was dead by 1994, it's alive and well and works all right, and nobody, people talk about the precise machine, they tell me, no, this is the competition. Says, no, this is their niche. So people say they have proof of stability. I'm laughing, say, for 6 to 8, you have a lot of proofs. But we don't need proof of stability here. This is not, it's automatic tuning, but it's fixed control. You have a gain, you run the machine with fixed control. Which was not adaptive control yet. I had adaptive control, but I was not sure mathematically that it is safe. That stability it's guaranteed. So I did this machine. Again, you have an automatic tuning, you replace the best control guys, tuners, with a button, but you use fixed control. Okay. But now I said what happens is the plant is not exactly known if you want better. Still, you do the tuning, not one tuning for all machines, but you do the tuning per machine. The machine itself is not exactly the same when it's hot, when it's cold, when it's longer trajectory, shorter trajectory. So you would like to have the right gain at the right time, at all times. So this is how we started thinking about adaptive control. Okay, this is why you need adaptation when you don't know exactly the parameters. You want to do for the machine the best control, and then the parameters change. Then you want to fit to follow the changes, so to keep the good behavior. So the first idea is very simple. You take your, not just input output, without folders, you have the model of your plant, you do some basic analysis, and you know that they are fixed, and then you check for different gains, you know that it's stable between 1 and 10, and you let the adaptive algorithm change the way you want it to change, but not to violate the bounds. So everything was all right. I take an example, and I want you to, it's stable, and you can show that in closed loop it's stable for different gains, and I show, can you, if you do the analysis, you see that if K is larger than 0 and smaller than 264, the plant is stable. So, but I don't want to play with fixed gains. I want to play with, to change the gains. Now, great names, genius. I take my hat off. Only must be careful. We always, when they It was conjecture, nobody proved. We must be very careful. So they said you can do it. And there were counterexamples. I looked at them, the counterexamples were bad. So I said, so they might be right. So let's try. They try for a fixed gain in the middle of the range. This is the response. I talk about stability now. For a low gain close to zero, not in zero because this is already the margin of instability, but 0.1 is slow, but it's stable. For 2.55 oscillates, but it's stable. So the system is stable for the entire interval, for any gain. So I said, if this is, again, I want to change it within the admissible, the so-called admissible region. So I take the gain with average, the middle range, 1.3, plus some sinusoidal function with some coefficient. If A is 0.8, then the gain is between, you can see here, 2.64 is the upper mark. 0 is here, so it's within the range. So it works. Try larger, it works. So I can say, gentlemen, you can do it. This is the problem of the time value systems. Nobody says that they don't work, but you must have the guarantee that it works, because otherwise a little bit of change within the admissible gain and everything blows up. As I said, this idea was used. That's what led us to a lot of theory. The word passivity comes immediately. We're going to explain. If you don't, you might know. And I managed to reduce it a bit to almost passivity. Some very great names left. Oh, they've been always. It's passive or it's been passive. But they didn't left. Some apologized to them. It took some 15 years, but it's all right. So how do you have passivity? The passivity is related to optimality. You have a linear system. You want to optimize it with the Q and R to do the best control. And you reach, this is the solution. I'm not going to teach optimal control. You know, we have a Riccati equation where you choose Q is the positive definite matrix, R it's also. So you try to solve this algebraic equation to find the positive definite, if it has the positive definite solution, has a positive definite solution P, and you use this state feedback. This is an optimal system. Now, I can show the closed loop system, it's already A minus BK. So this is the stability equation for the closed loop system. If you do the operations, you see that the closed loop system is stable. Not only stable, but it's a little bit more than simple stable. So the optimal control gives you a higher gain than the minimum stability. So what I said here, I just wanted to show that even half the gain would be all right, gives you stability. Not optimality, but the plant is stable. And I call this combination PB C transpose, because in some plants, you can have the plant that can be stabilized by a gain. It's not necessarily stable initially, but can be stabilized. The closed loop system is stable and also satisfy this condition. There are plants, and I'm going to translate it into good language, not general. Some plants are stable, satisfy stability, and the second equation between the input and output. In such plants, you can use, if the plant gives you a C, which satisfies this equation, it's a good output. You can use, for a single input, single output, you can use a scalar. It's not a matrix, not a matrix gain, it's just a scalar. So this is what happened. It's not BK, but BKEC. If this is just one for single, so it's just one number. In general, I'm talking about the same number of inputs and outputs. People say, oh, what happens if we use the control? We want a plane, we want to to control this direction, and so on. So you have each input must give you an output. They are connected in model, but when you have 3 inputs and 7 outputs, what do you want to do with this? All right. So I mean, single input, single output. The adaptive control doesn't go beyond it. The classical. I can go for 4 inputs, 4 outputs, 10 inputs, 10 outputs, but the same number. So this is the situation. This is a good property. And I call a plan that needs some feedback. I call not strictly. A plan that satisfies this condition is strictly posterior. If I don't have the gain, but I favor the plan without the gain, it's almost strictly posterior. Why do I need this? Because we can satisfy the conditions. Okay. Now, from what we get, if we write the CB equals CB or B, the CB transpose is the same thing. So CB must be positive definite symmetric. It's clear that this is positive definite symmetric, this is positive definite symmetric. All right. So as I said, the plant is called strictly positive real or strictly passive. The plant is strictly passive. Its transfer function is strictly positive real in linear time invariant. And the plant which is not yet, I call it almost strictly positive real. So it needs only a plant. What plants satisfy this condition? I'm going to show. There are plants we can translate this condition in a way that you can implement it. So there was the idea of model following. Model following, you have a model, you want the plan to follow the model. You want the plan, which means you have the basic idea. We start with the basic ideas, which I admit they are very good, even if I have to change them. But somebody needs the idea. I didn't have, as I tell people, God doesn't work here. I hope it's not against us, but we need ideas, good ideas. So they measure the error between the state of the model and the state of the plan and supply this gain, so given by what they say, and you have perfect, can be shown you have perfect tracking. Okay, but now I said what stability, what passivity means, the adaptive control. The first one was MIT rule, the simple one. Then they used the idea of linear model format that I explained, and this led to classical models of adaptive control, and I learned a lot from them. They're great names that I take my hat off to them. Astrom, Narendra, Lando, and many others, Kokotovich, and so on. But it was a little bit too much, so we tried to do something simple. So the MIT was very good. They just changed the lines according to what Kahneman and Eisenman said, and they worked very well. So the people, the pilots liked it because they know that their parameters changed, that the planes work in different conditions. So they put in a plane and it worked very nicely until the plane crashed. So for a few years, people didn't want to hear about adaptive control. But then the great guys decided, as I said, to do it. So one idea was to take the gain from the plan to follow the model. Again, the plan and the model are the same order. You take the gain from the state, and you can show that finally, if the plan is stable, just supply the command and it's going to work. So this was the idea that was followed by adaptive control. They decided to have the plan and to decide for good model, the same order. Again, the order could be 50, you have 50 gains. And the gain, this is the gain, k dot, we write in general this, but I like the integral to show you have an error, this is an error vector, and this is the state vector of the model. You do the correlation, E1 by X1 and E2 by X2. So if the error is correlated with the model, if the gain is not right for the specific X, if K1 is not right, then E1, it's not, that the K1 is not good. The error and the model are correlated. So the gain changes until it's better, until it reaches the right value, which gives you E0. The proofs are very complicated, very complex, but that's what they want to say. So the command takes the state of the model and multiplies by the gain. So again, if you see the adaptive control papers, the model is over 3, 4, it's already large. They did a lot of good Lyapunov stability analysis, but require some strictly passive condition and so on. And there are problems with stability. And also, so the problem for us was big. By 1980, to use for a flexible structure, such a plant was impossible. So we tried something simple. Tried something simple to make the practical and also to guarantee the stability. And then, so we use a low-order control, even a large system. I started with such a thing, not adaptive. I have a big system, and I use only the low-order controller, where I only use the velocity and derivative signal, and it worked. So this is the simple adaptive control. We wanted just something that can work because we couldn't implement the large one. That's how we started doing, and slowly we saw that you don't need the large one. Because, so the condition that we need, the basic condition, this is not that you have in the real world, the system can be almost strictly positive real. So there is a gain that can stabilize it, and the BC satisfies this condition. So the system can be stabilized by some unknown gain. Why do I have this almost strictly positive real or almost strictly passive? The plant is almost strictly passive. Its transfer function is almost strictly positive real. It's called strictly positive real, almost strictly positive real. But in nonlinear system, time varying, you don't talk about the poles and zeros, so it's strictly passive and almost strictly passive. But this is the condition. Why? Because I can show what systems satisfy this one, and if they don't, how to make them satisfy. If the plant is like this, the first idea is to use the gain E square, to integrate E square. Again, you know that the system can be stabilized by some gain. If it's strictly positive real, if the gain is larger than the minimum, the system remains stable. This is the idea of passive system. If you make it, so the gain increases with the error as long as the error is not zero. When the error disappears, then the gain is fixed. You don't have anymore. So this is the basic main gain, and it works unlike the MIT rule, the simple varying gain of the system works. But we know that it's better to have the gains from the state, from the plant. So we use the plant state and the input. And that's how it's always a correlation between what you introduce, what you use, and what you have. We use the error, we use the tracking error. We don't need the plant to follow some states of the model. No, we have some good comments as we started, and order 3, 4, 5, and the plant can be order 70. They still have those 3, 4, 5 gains. This is, in short, the adaptive control. The simple adaptive control. You have the error, the tracking error that changes the gains according to the situation, and assuming that the plant is almost strictly positive real. Which means, as I said, I don't go over everything here. People who are interested can see, but this is the lemma. The plant is minimum phase, and CP is positive definite symmetric. For single even single output, CP is just a positive number. Such a plant is a SPR. I would say minimum phase and relative degree 1. This is what it's introduced here. CB, the condition required, this condition CB positively symmetric, I didn't like the symmetry, and I observed that if there exists a W, if CB is just positive, definite, not if CB is real and positive, if the eigenvalues of CB are real and positive, this plant is almost strictly positive real. I call it WASP because it doesn't have to be symmetric. But we can keep the almost strictly passivity without requiring symmetry. So the idea here is that you use a plant and you can show that there exist some fixed gains. If they have the fixed gains, then you reach the ideal situation that follows tracks the model. The output of the ideal situation tracks the model. This is the ideal gain. So this is our real plan. And you do the adaptive control and see if you can show that this ideal plan exists, and you talk about the tracking error, the state tracking error, and you have the idea that we don't have a model. It's just the ideal situation of our plan. Is the difference between the present plan and the ideal plan, and we wanted to go to 0. This is the adaptive control, and with all the rules. Now we go to the nice Lyapunov, which is a great idea. You just must find a positive definite gain. If you work in adaptive control, you know that you need a positive definite function of the error plus a positive definite function of the adaptive gains. They are both changed. They are both dynamical values. You do the derivative of the Lyapunov function, and by a lot of work, you reach that the derivative is of this. So it can be only negative or 0, but the gains don't appear. So such a result is called positive, negative, semidefinite. The derivative is negative, semidefinite. So you don't know what the gains do not appear here. It's not a Lyapunov. So here there are many problems. You don't know how exactly what to do. So it requires a lot of conditions. So I said we had some LaSalle's works. No, they said no, LaSalle doesn't work for system with input, the system with time-varying parameters, only with the systems which we'll show immediately. Now again, nonlinear system have the same situation. We want the Riccati equation looks the same, but it's a differential Riccati equation. That's all. This is the difference. It looks almost the same, and you can extend it. And I had to use it for manipulators, which are, if you go for large gains, things become sinusoidal, cosine, and so on. They are nonlinear. And almost strictly passive is the same. The system with some unknown gain can become positive, strictly passive. What happens? But you don't see almost passivity in the world. So the one idea was that we observed at some point that if K, you have a gain K that does stabilize the poles, then add to the plant something in parallel, the inverse of this gain, and you have zero plants. So this is, the plant is stable, not stable, it has stable zeros, could be stable, this is not important, a stable zero, and the relative degree is zero, which still works. I didn't talk it because we don't want it. So this is the first application. So if you do it, you see that if you try, you see that you are going to get stability. Can be proved. Then the problem is you do add something in the parallel with the plant. What they say, let's assume that the plant is G and assume that it's such that maximum is 1. So the error can be shown, the tracking error, it's 1 over upper G from the command. So if G is 1, then the command, the maximum, then the error is half of the command. But if you use a gain, instead of G, you use 100G, then the error is reduced 100 times. But would require the high gain 100 that forces the move. So instead of 100, I'm going to put 1 over 100 in parallel, and can be shown, you must read the papers, I'm not going to try to convince you, that this more addition in parallel with the plant, well, this is the inverse of some gain that stabilizes, maintains stability. So, but instead of using high gain, you stay with the gain, and you have a plant that gives you a smaller error. And so, this is the first idea. I try to play with this, the same algorithm, the same plan that tried, but I didn't like now. After the first idea, I didn't like to have a direct input-output because it's a short circuit, actually. It gives you an algebraic loop. But now I'm looking, in general, a plant is good if you add to the plant some controller to make it even better. And a good controller, in general, you need damping. So if you have the position you measured anyway, so if you add some damping, a PD controller could be good. Better than a constant. Now, instead of C, I'm not going to add a controller, but I add the inverse of this controller. It's just a simple first order pole, and I get a total plant, an augmented plant, that the gain can be variable. This plant is almost strictly positive real, so the gain can make it strictly positive real, strictly passive, and start playing. Gain 1, 2, 3, I play to 1, 2, then it diverges. Here I'm playing, I'm not going to talk, you want to see what happens. I played with the gains. So I took the gains not 1 to 3, I started 1 to 3, and I read 10,000. This is how the gain works, and this is how the plant behaves. This is augmented output almost perfect, only with the changes when we do the computations. And this is the actual plant, and it remains stable, no problem, no matter how the gain. So again, what I wanted to show that we have a plant. If you can stabilize it, you must know something. People tell me, no, adaptive control, we don't like adaptive control. And I ask, are you doing something else? Yes. Okay, if you do something else, then you can guarantee stability for adaptive controller. If you can't guarantee stability, the performance is going to be much better than you can dream. So again, the small PFC, if you need a high gain, the PFC is going to be small and don't require high gains. And we didn't expect it, we didn't want it, but we observed that also the disturbances are reduced, the noise. We assume that the design of some stabilizing controller is feasible. I want a controller that can stabilize the adaptive gains I showed. I want the plant to be stable. the right feed-forward gains, if the stability is guaranteed, can give you performance without requirement. So I don't try much. I want you to be able, I was asked about the nonlinear system. You must know something. I don't take any nonlinear system and stabilize. No, you must know something that you can stabilize it at least. Then performance we can obtain. So this is the adaptive control. Here I wanted to say, this is the gain, the adaptive, the integral gain. This is the k dot of x, k dot of u, k dot of e is the e squared, or e transpose, minus sigma k. Why? Because the error, for a sigma equals sigma r, you have the integral of e squared. The error can go down very much, but then you have a least significant bit that still gives you error. Then the gain keeps increasing. Or for any kind of disturbances, you have a gain, the error is not zero. Then this gain increases. It might blow up, can go to very high values. No, I don't want to go to very high values. No, I do not need it. So the gain becomes too large. We have this term. This was a term introduced by our friend Matrosov. I hope you know the name. And then people told me, no, in a rand it appears something, the Russian said something. Okay, but I take my hat off to people who had ideas before, but Matrosov put it to work. And I loved it and I put it. I have it here. In the beginning I put it on all of them, but here we don't need it. It can be shown if you read the papers that those gains are some gradient minimization algorithm. You have the relation, the correlation between the error and the x, and the error in the input. So even if you have noise, it's going to be some minimum value, some medium. It does not diverge. So if I put the sigma here, I had some worse performance. This is good performance. Those are the real gains. In the beginning, we also use some practical gains. Why? I get some proportional gains, not only integral. Because we started with adaptive control, the general adaptive control, which required slow adaptation. No, we don't have to be slow. We don't need it. I don't use it anymore. So the gain, the integral gain is the total gain today. So as I said, this is the principle, the planting principle. Practically, we don't add anything to the plane, we only measure. So this D in the feedback has the same role because we want the adaptive control to see a plant which is ASPR, ASP or SPR. Okay. You need the idea how to use some stabilizing controller. With relative degree 0 or 1, or if it's not relative degree, take 0 or 1, take only this part. The lead leg, take the lead, make it the inverse in parallel, and leave the leg there. So just I want the D that we had in parallel with the plant to have the relative degree 1, which gives us the ASP situation. And here we show a little bit. Application to a control system. This is some computation, what you did. I don't think, just I wanted to show you a plant. And add that's how it looks. You have some initial gain, and you add it could be 0 if you don't know something else, but you have some gain that you know how to stabilize. And that's how it looks. I leave this for you. This is adaptive gain, and we tried the adaptation for the plant. This is the controller that it could be, and therefore the D appears like that, and that's what you get. The original system, This is, okay, sorry, this is the plant with the controller, this is the plant, and the best thing is this one, the response, this is the error. And we do the same thing with adaptive control. As I say, without proportional adaptive gain, only integral gains. And this is the result. The required and the given. The error is something else. You'll see here the error, but this is how it looks compared with the plan. They're almost perfect. Okay, so again, this is the step input to the model. The desired response is this one, and the plan follows this exactly. The problem is that in the non-linear, in the real world, you have a lot of problems. Lyapunov requires negative definite derivative. In realistic plans, you have semi-definite at most, very difficult to find. And they require a lot of problems. You see almost all things appear as uniform continuity of the Lyapunov derivative, which means uniform continuity of the plan. If you open a book, people don't even know. Why do you require continuity? No, you require continuity. You have the differential equation, meter divides y dot equal x dot equal f of x, then f of xt is continuous. So it's very nice, very good papers you can write, but talking with the people in the real world, they say, what continuity? Yeah, put the step. It doesn't work. I don't need any adaptive control. So in the beginning, there was an invariance principle that we called in the West LaSalle, but the Russian introduced, showed that it was introduced by Bashin. So you have this plan, no time. The time does not appear. The derivative is, but in the function, there's no time. This is called autonomous. No control, no time varying parameters, nothing. Then it can be shown that if the derivative is negative certainly, that then things tend to v dot equals 0. But what about f of xt? What about control signal? What about time varying plans? No, doesn't work. This is called non-autonomous. So you cannot use LaSalle's by the invariance principle. Sorry, you can. But people use the Barbalat Lemma, which you should, I think you know, requires some tough continuity conditions. It happened that by 1980, I discovered the book by LaSalle. And I started using it. I was sure that everybody is using it. I was wrong. Comes out that people the world didn't know it. So most people start with Barbalat Lemma. And I looked there, and then, because I had a paper which I wanted only to talk about LaSalle's direct principle, I called it, give it the, and there was, the paper was rejected. I just wanted to present LaSalle. So the paper was rejected, and I wrote it again. And then I saw that not only I can explain LaSalle's better, but also to eliminate some of the problems that still LaSalle talked about. And this will have a new invariance principle. And then I saw that we can come with a new theorem of stability. But first of all, most papers in adaptive control use a Barbalat Lemma, which says that if h of t has a finite limit, if h of t has a finite limit, then the derivative must be 0. They say no. No. Only if the derivative is also uniformly continuous. Then the derivative tends to 0. Why? Because they have counterexample. They tell that the logic is not enough. For example, even if the derivative goes to 0, it does not imply that f of t has a finite limit. This is f of t, sine, it's a sinusoidal. The derivative is this one. So of course the derivative, t goes to infinity, the derivative goes to 0. But the sin, they say, keeps being going up and down. All right. So for this one, I'm telling you, if you read ln of t, the derivative of ln of t is 1 over t. So the derivative is like this. So that's why the slope, ln of t goes up, but the slope reduces, it tends to 0. So the sine of ln of t, it's a function of period that goes larger and larger. You can show that if ln of t tends to infinity, the period of the sine becomes infinite. What is a sinusoidal wave with infinite period? Okay, it's a constant. So the counterexample is not very much, but much more difficult was the other. You have a function that has a finite limit, but the derivative doesn't go to 0. So this is the function. You use the derivative function formula, and you get this. First, what about this? So you have two terms. This one disappears as t goes to 0. But the first one keeps going up and down. Here we must review stuff. And you plot it, and you see that f of t, the oscillation becomes smaller and smaller, but the derivative keeps going up and down without doing anything. This is even more difficult. Okay. So my paper was rejected by such an example. A paper of mine. We have the derivative of a function has two terms. One is a continuous function, simple function. It's negative, goes to 0. It will be the, let's say, and ht is 0, it's only the discrete time sequence. Sequence of 0 just spikes. So the integral of a spike is 0. So therefore you have the derivative with the spikes. You integrate the derivative, you get a nice function that tends to 0, but the derivative doesn't go to 0. So my paper was rejected, and I didn't know how to. Okay, it was rejected. I wanted to say, so it doesn't work for such examples, but doesn't kill everything. But I didn't have that. But then let's see. This is the function f of t, and this is the integral. Okay, wait a minute. This is even more difficult. I'm not going to talk. And I'm going to treat this one later, and I'm going to show why the counterexamples are wrong. But if you have a continuous system, if the derivative is continuous, then your function is v, you must show that it has a finite limit, and then the derivative, it goes to 0. So in such a case, we have no discontinuity. So the error goes to 0. So in the beginning, people were very satisfied, but then you read from people, LaSalle himself, no, didn't like these results. But I used LaSalle, I'm going to present it now, and this is does not require continuity. But people said, I can kill all your proofs, a great guy with a tiny amount of discontinuity. I said, but what will you do? You do adaptive control, but any nonlinear system can blow up because of discontinuity. We have LaSalle invariance principle, that's what we have. They said, no, it doesn't work. Actually, I had the LaSalle invariance principle in 1980, which was like this. First of all, we showed that you don't need continuity like this. So let's take this counterexample, this supposed counterexample. The integral of g is something, the integral of h is not. Come on. So the integral of f is actually integral of g. If the integral of h, if h does not appear in its integral, how can it appear? How can it appear in the derivative? No, sir. No, sir. The derivative of the f of t is the derivative of the integral of g. Is g, not f. So this, be careful. We call our differential equation differential, but it's not a derivative necessarily. It's only an integrator. The part that appears in that gives you something in the integral is the derivative. The other parts are not. Also this one. The formula is correct. But first of all, let's think. Sine of t squared, it's a sine with an ever increasing frequency. It becomes some spikes. And the spikes become denser and denser. You end having a bunch of infinitely dense spikes, not exactly differentiable. Besides, that's what they say. Must think a little bit. Besides, the derivative, it's a local operation. We learn, we forget because they have the general formulas. But the derivative at any position, it's contained by this. It's obtained by this formula. If you supply this one, if you compute, you are going to see that the formula, the operation doesn't work for t goes to infinity. So because the local derivative, okay, so this is the good formula. Even if it exists everywhere, it gives you a t equals 3, the same thing that this formula. The general formula doesn't take that the local formula is not, it's bad. But the local formula, when you can obtain, gives you the right response, even if the general formula doesn't work. So if I have problem with infinity, and then I compute limit for any t0. You have a function that the t0 doesn't have derivative, it's a spike. But for t to t0, it works. So you can compute for any t0. The problem, the step is that you must be able, and people who I gave it to lots of professors, they say, oh, this is not derivative. But there are papers were rejected, but there are people who can read, and papers are accepted. So you must get used to the idea. Then for the derivative, when t tends to infinity, you must compute the local derivative for specific condition, not a general formula. You take the limit for t to infinity, and now, if this one tends to 0 and this one tends to 0, then the result is 0. So, what I'm showing here, by using the local derivative, shows that if the function has a finite limit, the derivative is 0. Now, this is very delicate, things were rejected. Fortunately, people were able to explain things are explained. I don't have time now. The counterexamples are very smart, but they don't really check. They use the formula without checking that when you do the derivative, the formula does not work. If you look at my papers, you are going to see that using the derivative, it shows clearly that the formula cannot be used for t short to infinity. But if this function would be problematic at infinity, we would have I could not do this for sine of t squared. And you'd see that you cannot do the derivative. But sine of t squared by t and sine of t plus h squared by t plus h both go to 0. So you have derivative. So again, the optimists work very hard to prove. Let's say those are continuous and you have a lot of good papers. But people say no. We have problems. Impulsive control, hybrid system. The system is continuous, the plant is continuous, but the controller is discrete. So you don't talk about continuity. Even the proofs of in simulation are digital, and you don't have any continuity. So they prove. All right. So this is solved not. If the function reaches final level, then one is derivative. Okay, this is some thoughts. The real invariance principle, if I show that the counter, by the way, there is a LaSalle's proof, there is my proof, nobody said that your proof is wrong. They come with counter examples. So, going back to LaSalle, he requires a condition. You must check that the integral of the derivative, this is the function, the integral for any finite integral is less than some limit. And this is, for some reason, LaSalle talked about the modulus of continuity. Mu of b of a, it's a continuous function of b minus a, of the interval. So the integral, the trajectory, the length of the trajectory increases. You see how much you pass, increases with the interval, but cannot be infinite for a finite time. If it cannot be infinite for a finite time, then he also requires the derivative, which is a function, can be a function of time, to be less than a function which is not of time, negative semi-definite, and then the conclusion then goes to 0. And again, the derivative, it's in our adaptive control goes to 0, so, but here we don't have continuity. The derivative, v dot of t, it's 0. What happened with LaSalle? There are a few problems. First of all, for some reason, he had this modulus of continuity, and also required to find the function that can be. So for some cases you can do, for some cases you cannot. For this case, I don't think I should spend time. For such a function you can write, for such a function you cannot. And still, this function is negative semi-definite. This function is negative semi-definite. So I decided to extend it, to eliminate. So again, v dot tends to 0, and people are very satisfied, assume got some kinds of conclusion, but Lyapunov, LaSalle himself showed that it's not exactly clear. Where does it go? What happens? Tends to 0, go to 0 to stay 0. What happens? You have a system with two variables, and this is the Lyapunov function, but the derivative is only one variable. So x2 goes to 0. All right, what does it mean? x2 goes to 0, can be like this, uniform, can be like this, can be like this, x1 is doing what? And can be also like this. Tends to infinity, but on the way is doing a lot of things. And even this one. This is not my observation, so it's not very good. What can you do? Or try another equation to give another situation. So I gave an example of order 2. Can be example of order 5, where the result is also that one variable goes to 0. What happens in all the others? You need 5 Lyapunov equations, and now here the new invariance principle. I only assume I don't need any, for my proofs, I don't need any model of continuity, just its boundary. Then this again, for any integral for a finite interval, it's bounded. Which means that you cannot pass, the only thing is you cannot pass an infinite distant finite time. So the derivative is negative semi-definite without requiring a condition, and this says that you must end with v dot equals 0. The first idea was that some point end with v dot identical 0, which means you remain there. You go to 0 to stay 0. This is how I denote it there. I'm going to denote further. But then I didn't like it, so we can go on. So the same condition, trajectory exists, and f of t is bounded about the trajectory of any finite interval. And the derivative is negative semidefinite, normal. Then all trajectories end asymptotically in a region where the derivative vanishes, tends to 0. And as I showed, if a function changes, the idea is that the derivative is negative semidefinite. This can be only negative for 0. If it's negative and not 0 for an infinite distance of time, then the v dot should go to minus infinity. Cannot. Therefore, it stop to 0. The Prof is not wrong. The counter example I'm trying to show. But now, as I said, the velocity goes to 0. If the function reaches a constant limit, then derivative is also 0. Then if v dot goes to 0, then the derivative is the second, and so on. So, you can have a system of 50 equations. The derivative gives you only minus x1 squared equal negative. So you know the x1 goes to 0, but also x1 dot goes to 0. So x1 dot an equation that gives you a relation. So you can have 50 relations for the 50 variables to know what happens with the system. So if the system is asymptotically stable, you get it. If you have some limit cycles, you get it. Proof, I'm not going to show it. I leave it here for people who are interested. Feel free to read and to talk to me. I think I'm going to finish. All right. I think I finished. Just want to say that this equation may be misinterpreted. So I am only assume that the limit set is such that where v dot of x of t tends to 0, the limit for t is infinity equals 0. Because you might have some terms that they're not alike. Okay, to make clear, like such a counter example, if by very simple equation, if you solve it, you see this is the equation. So you start at any x for any x0, you start with x0 plus 1, and then end with x0. So any point is an equilibrium point. But they say that v dot, if you select this function positive definite, the derivative is this one, but cannot be 0 for any time t. So LaSalle with this, everything is wrong. I say no. You must define the equilibrium point not as f of xt equals 0, but at line limit for t to the infinite, and therefore those are the limit points, and this is the equation. This is the terrible equation. A terrible equation where they say everything here is continuous, but for some reason the position gets some changes. The position changes. And they use the impulsive controller out of theorem and say, okay, how is the velocity continuous if the position jumps? So I say, no, it is not continuous. It has, these jumps are due to some delta function. And after Dirac, so long after Dirac, we can do it. All right. And the derivative comes negative definite, we have simple stability. Okay. So I didn't care if I took some square wave and I showed that things converge. Just an adaptation of early adaptive control. So the adaptive control works and it's stable under the condition, know how to stabilize, and they played with machine. They did the best controller. So that happens that this is the desired projector, this is the nominal This once again changes, that's what you get, some big error. And you use adaptive control and you get this. Okay. So I took another example, UAV, nonlinear phase, that has a nominal situation and can reach some other situation. So people tried some controller and the PID, nice controller, and fuzzy, and this is what they got in the nominal situation, 3 situations. And in the deteriorated situation, this is what you get. This is the best that you can get. So I use the adaptive controller. As I said, put a parallel feed forward, just to show you the print. They can be seen that some PD, as I said, in general, we can try something else, but here PD work. So the inverse of PD is the PFC, and this is what you get. Of course, the augmented system follows nicely, perfectly. I mean, the real one doesn't work. This is a nominal case, this is the desired, this is the nominal case. The nominal case and the external case, the adaptive control works. This is the nominal case, the best nominal case, not to talk about the other one. I have a large flexible structure, and you have a lot of problems. You must put, this is where you go. This is how I worked in the beginning. We put some flexible, some derivative feedbacks and so on. You have to must take care of noise and disturbance and so on. Instead of this, a simple PFC, low gain first order pole, eliminated everything and things work. You can see it in the papers, and also a more general situation. You have a plan, you can show that the controller stabilizes it, makes it all right. Then instead of this, we put something in parallel, and I use, in order to fight continuity, I use square wave command. This is the perfect tracking of the augmented system, and this is the real one. All right. That's what I have to say. So you try not to reach limitations, because there were adaptation cannot work, doesn't give you anything. Proper field forward tuning gives you good trajectory without trying to squeeze the system. All right, I'm done. You have a lot of papers. See them, feel always free to call me, to write to me, to ask any questions. I think I'm done. Thank you. I don't hear. No. Something happened with I think it's your speaker, your microphone. I don't know what happened. I don't see you now. What happened? Something is wrong. Something happened. No. I think we'll stop. I say thank you. I hope you get something. Have a look. I can tell you just one thing. Things work, and they are guaranteed to work if you satisfy the conditions. So feel free to ask me anything. Aspettando. What happened? It was so nice. No, I don't hear him. Sorry. Why don't you use Zoom? Zoom works, and also Teams. I don't know what you are using, but we had some problems. I'm here. If you want to take time, I'm here. If not, we let the people ask the questions by email. So we are done? We're finished? Okay, just a second. No, your microphone is off, I think. I see a red line here. Your microphone, okay, now it's on, but I don't hear you. I cannot hear you. Sorry, very sorry. No, don't know what happens. No. Something happened now. It used to be so nice. Okay, so feel free to write anything you want, to ask whatever you want, and I hope it was not in vain for any people. And people you don't be afraid to ask questions. You don't have to show knowledge when they ask a question. And any objection, any problem, anything that seems wrong or not understood, I'm glad. As for the young people, having your paper rejected, it's not a pleasure. But look, if somebody just rejects your paper, this is hostility, not review. But when people ask, here is wrong, look there. You may need to correct, and in my new papers, I acknowledge, I'm thankful for people with the right criticism, because it forced me not only to explain better, but even to develop new stuff. So that's it. Now, thank you very much. It was my pleasure to talk with the Brasileiros, and let's hope for the best. All the best. Thank you very much. Bye-bye.